Structures constrain their own parameters. How systematic structures constrain their own parameters. Developed by Malaelu. Date, September 15, 2025. The core question, instead of asking why are physical constants fine-tuned, we should ask, how do systematic structures force their own parameters to take specific values for internal consistency? Mechanism 1. Circular constraint networks. How it works. Parameters in a system are not independent, they form circular dependency networks where each parameter constrains others, which in turn constrain it back. Example, the electromagnetic system. Greek letter alpha, fine structure constant, determines electromagnetic coupling strength. Coupling strength determines atomic scale and stability. Atomic stability determines what electromagnetic interactions are possible. Possible interactions determine what coupling strength can exist. Result. Greek letter alpha is locked into 1/137 by this circular constraint. Example, planetary orbital systems. Orbital period determines gravitational influence on other bodies. Gravitational influences determine orbital stability. Orbital stability determines what periods are sustainable. Sustainable periods determine orbital architecture. Result, only specific orbital period ratios create stable multi-body systems. Mechanism 2. Scale bridging requirements. How it works. Systems that must function across multiple scales are constrained by the requirement to maintain coherence between scales. Example, quantum classical boundary. Quantum scale, set by h with stroke, must connect smoothly to classical scale, set by everyday objects. Connection point occurs at electromagnetic scale, set by Greek letter alpha. Greek letter alpha must be 1/137 to create a bridge zone where both quantum and classical physics apply. Too small, no bridge zone. Quantum effects disappear abruptly. Too large, no bridge zone. Everything is quantum, no classical behavior. Example, biological information processing. Molecular scale, chemical bonds, must connect to cellular scale. Metabolic networks. Connection requires specific energy scales that allow both stability and flexibility. Energy scales constrain chemical bond strengths and reaction rates. Result, biochemistry parameters are locked by the requirement to bridge molecular and cellular functions. Mechanism 3. Complementary balance requirements. How it works. Systems containing opposite or complementary aspects must maintain specific balance ratios for stability. Example, nuclear forces. Strong force must be strong enough to bind nucleons against electromagnetic repulsion. Strong force must be weak enough to allow nuclear variety, not turn everything into one giant nucleus. Balance point creates narrow window. For nuclear diversity. Result, strong coupling constant is constrained by the requirement to balance binding versus diversity. Example, stellar nucleosynthesis. Gravitational collapse must balance radiation pressure. Nuclear burning rate must balance energy loss rate. Balance requirements constrain stellar mass luminosity relationships. Result, only stars within specific mass ranges can create heavy elements. Mechanism 4. Emergent constraint feedback. How it works. Higher level structures that emerge from lower level parameters then constrain those same parameters through feedback loops. Example, atomic chemistry constraining. Greek letter alpha 1, Greek letter alpha, determines electron orbital structure. 2. Orbital structure determines what chemical bonds are possible. 3. Chemical bonds determine what molecular structures can form. 4. Stable molecules create selection pressure for specific Greek letter alpha values. 5. Only Greek letter alpha 1/137 allows the molecular complexity that creates stable matter. 6. Stable matter is required for the system that contains Greek letter alpha. Example, galactic structure constraining dark matter. 1. Dark matter properties determine large-scale structure formation. 2. Large-scale structure determines galaxy formation efficiency. 3. Galaxy formation determines star formation rates. 4. Star formation determines heavy element production. 5. Heavy elements are required for planets and complexity. 6. Complex systems are required to observe and constrain dark matter properties. Mechanism 5. Information theoretical constraints. How it works. Systems that must process, store, or transmit information are constrained by information theoretical requirements. Example, quantum information and Planck's constant. Information processing requires distinguishable states. Distinguishable states require minimum energy differences, set by h with stroke. Energy differences must be large enough for stability. Small enough for accessibility. Optimal information processing constrains H with stroke to specific range. Result: Planck's constant is set by information processing optimization. Example: DNA replication fidelity. Genetic information must be stable enough to preserve across generations. Genetic information must be flexible enough to allow evolution. Balance point constraints chemical bond energies in DNA. Bond energies determine mutation rates and repair mechanisms. Result: DNA chemistry parameters are constrained by information processing requirements. The meter pattern, self-organizing constraint networks. All these mechanisms share a common structure. 1. Parameters create structures. 2. Structures create functions. 3. Functions create requirements. 4. Requirements constrain parameters. 5. Loop closes. Only specific parameter values create structures that create functions that create requirements consistent with those parameter values. Why this solves the fine-tuning problem. Traditional view: the universe got lucky with its parameters requires external explanation, multiverse, design, etc. Systematic constraint view: the universe's structure forces its own parameters. Explanation is internal to the system itself. Parameters aren't inputs, they are outputs of systematic requirements. Testable predictions: if systematic self-constraint is real, we should find 1. Parameter correlations. Physical constants should show unexpected relationships reflecting their systematic interdependence. 2. Constraint hierarchies. Some parameters should be more fundamental, more constrained by system requirements, than others. 3. Emergent stability. Systems should become more parameter stable as they become more complex, more constrained loops. 4. Universal scaling. Similar constraint patterns should appear across different types of systems: physical, biological, social. Implications for physics. This perspective suggests physical constants are solutions to systematic constraint equations, not free parameters. The universe is self-solving, its structure determines its own parameters. Fine tuning is actually systematic inevitability. The deepest physics isn't about finding the right equations, but understanding how systems constrain themselves. The philosophical revolution: instead of asking why is the universe fine-tuned for us, we ask how do systematic structures organize their own parameters for maximum internal consistency. This transforms the universe from a machine with mysterious settings to a self-organizing constraint network that inevitably creates the parameters necessary for its own stability and complexity. The answer isn't that we're special, it's that systematic self-organization is universal, and we're one expression of the universe's inherent tendency to constrain itself into increasingly stable and complex forms.